Okay, welcome to Success Tutorials. Today we'll be looking at organic chemistry, introduction to organic chemistry. So this class is breaking down organic chemistry from the foundation, step by step for you, to your understanding. And in this class, we already have an outline of what we'll be covering today. If you're just watching this video and you have a foundational issue in organic chemistry, you've always had issues in understanding the key concepts in organic chemistry, this class is for you. So stay tuned and enjoy the class. Today I'll be starting with the foundation, which is the definition, history and importance of organic chemistry. So we'll go delving into why organic chemistry was studied as a course, as a topic. After that, we'll then be looking at composition of organic compounds. Organic compounds are derived from organic chemistry, of course. So we'll be looking at organic compounds. And then we'll also be looking at qualitative and quantitative analysis of organic compounds. We're looking at qualitative and quantitative analysis of organic compounds. Then we'll go to empirical and molecular formula of organic compounds. Yeah, just like we have the inorganic chemistry, we have organic chemistry also has empirical and molecular formula of organic compounds. Then 4, we're looking at index of hydrogen deficiency of organic compounds. We're taking a look at index of hydrogen deficiency of organic compounds. And 5, we're looking at introduction to alkanes and alkynes. I'm sure you must have seen these key families already. You must have heard of them one way or the other. So these 3 families form the foundation of organic chemistry. Now, if you can know these 5 first key aspects of organic chemistry, you would have built your foundation in organic chemistry, and then you can forge ahead from there. So the essence of this class is to introduce you to the basics. This class is for a beginner in organic chemistry. You have always had issues with understanding organic chemistry, maybe from your secondary school. Maybe you were not taught well, or it was not well broken down to you. This class will help you understand organic chemistry from the foundation. So without wasting more time, let's start now. We're going to be starting with definition, history and importance of organic chemistry. Now for the definition, let's start with the definition then. So we're looking at the definition. So of course, if you want to study a course, it's very vital that you can at least define what you're studying. So that's why we're starting from the scratch, the definition. So when looking at organic chemistry, class, you can write down. Now, organic chemistry is the study of organic compounds and their derivatives. Organic chemistry is a study of organic compounds and their derivatives. So this is the simplest definition of organic chemistry. Because if you're looking at chemistry, chemistry is broken down into 2 broad categories. We have the organic part of chemistry and the inorganic part of chemistry. So to define organic chemistry, say organic chemistry is a study of organic compounds and their derivatives. Now, you won't fully understand this definition until you understand the meaning of the word organic. You will not fully understand this definition until you understand the meaning of the word organic. Now, when you hear the word organic, what comes to mind? The word organic means naturally occurring. The word organic means what? Naturally occurring. So, in life as a whole, we have 2 types of substances. We have substances that are naturally occurring, and we have substances that are non-naturally occurring. For substances that are non-naturally occurring, we call them inorganic. That's why I said that chemistry can be broken down into 2 broad aspects, organic and inorganic. Now, inorganic substances, on the other hand, are substances that can be artificially manufactured by man. Artificially manufactured or produced or processed by man. So if I'm using the word, let's use artificially produced. Normally, the real meaning of organic is something that cannot be made by man. That means you are naturally occurring. For example, we came as human beings to meet the plants. We came to meet There are some materials or substances that we just came to meet them as they are. They were not synthesized by man. Those kind of substances are called organic substances. While those substances that are artificially produced or formed, that means man-made substances, are inorganic substances. So when dealing with organic chemistry, our focus will be on naturally occurring substances, naturally occurring compounds. So if we say organic chemistry is the study of organic compounds, it means organic chemistry is the study of naturally occurring compounds then. Because organic means naturally occurring. So an organic means naturally occurring. So organic chemistry therefore can also be said to be the study of what? Naturally occurring compounds. Please take note of that, very important. That's why if you notice when we were looking at the other part of chemistry, the inorganic part, you see substances like H2SO4, hydrochloric acid, H2SO4, that's sulfuric acid, HCl, hydrochloric acid, and the likes of them. Those substances can be made in the laboratory by scientists. But when looking at substances that cannot be made in the laboratory by scientists, that means they were just found naturally. We term them what? Organic. If we have to give examples of organic substances, comparing them to inorganic substances. For example, your Coca-Cola, your Coke you drink, or your Pepsi. This was a man that made Pepsi, Coke. Your juice, your wines, they were made by man. When you come to your palm wine was tapped from a natural source. So those palm wine is a naturally occurring drink. So you see the difference between organic and inorganic. Now, moving forward. Now focusing on organic now. As we said, organic compounds are naturally occurring, but class, going to the history of organic compounds, there are some scientists that disprove that fact. Because if you say something is naturally occurring, then it shouldn't be synthesized by man. But class, we have a scientist known as Frederick Wohler. In the year 1828, disproved this theory. These scientists disproved this theory of organic compounds being naturally occurring. Because if we say organic compounds are naturally occurring, it means that it cannot be synthesized by man. But class, Frederick Wohler in the year 1828 was able to synthesize an organic compound for the first time. And what organic compound was synthesized was urea. Class, urea is going to be an organic substance because it is a major component of the urine, which is a waste product from when we urinate. This is a major component of your urine. So urea is from urine, and urine is a naturally occurring substance. Nobody produces urine normally. So therefore, if urea is from urine, urea is also a naturally occurring compound. Urea is an organic compound, and before this 1828, urea could only be gotten naturally from urine. But class, this scientist was able to produce urea from a rearrangement reaction. All these things I'm saying are in your textbook. From a rearrangement reaction involving a substance, an inorganic substance. That's what makes it more interesting. It produced an organic compound from an inorganic substance. Ammonium cyanide. Ammonium what? It was able to make ammonium cyanide undergo a rearrangement reaction to give urea. Ammonium what? Cyanides. So therefore, once this reaction took place, our whole definition of organic compounds had to change then. Because if this can happen, then we are wrong to say that organic compounds are naturally occurring. Because the scientists are able to produce an organic compound. So we needed another definition for organic compound class. We needed another definition for organic. Because if you say organic compounds are naturally occurring, meaning that they cannot be synthesized by man, how was Frederick Wohler able to now synthesize an organic compound then? So class, in today's day and age, if you ask to define an organic compound and you come out and say organic compounds are naturally occurring compounds, I put it to you that you are wrong, because not all organic compounds are naturally occurring. Some can be synthesized. And for a definition to be correct, it has to be absolutely correct, without any exception. So therefore, of course, it's not still all organic compounds that you can produce. Nobody is able to produce palm wine, natural palm wine. Natural one, not artificial one they mix anyhow. But as long as a particular organic compound has been produced by man, you can no longer say that all organic compounds are naturally. So for a definition to be correct, it has to be true for all cases, in all cases. So So therefore, we have a better definition of organic compounds now, class. We have a better definition of organic. So please do not forget the scientist named Frederick Wohler in the year 1828. He was able to synthesize what? Organic compounds. And disproved our definition of naturally occurring organic. Now, so there's a better definition for organic compounds then, class. This definition has not failed, has passed through the test of time and has not failed. And that definition is simply put, the organic compounds are compounds, carbon-containing compounds. Carbon what? Carbon-containing compounds. Class, we have been able to find out that there is no organic compound that does not contain carbon. So therefore, this is a more holistic definition of organic compounds. Organic compounds are carbon-containing compounds. All organic compounds contain carbon. All organic compounds contains. So we can say that organic compounds are carbon-containing compounds. And this definition has passed the test of time till now. No scientist has been able to disprove it. If you don't see carbon in a compound, you are not allowed to even call it organic, class. Organic compounds are carbon-containing compounds. If you're still following this class, please stay with me. Because many people, why they have foundational issues in some courses is that they don't have the patience to follow through the foundation, work on the foundation. When the foundation is good, then you can understand other tough topics. The mistake most students make is that they just want to go to the tougher topics immediately without building their foundation, a strong foundation in the beginning. This is where, these are the kind of things that you need to learn that will prevent those issues you used to have in those bigger topics. So understanding this is very, very vital. So let's forge ahead. So organic compounds are carbon-containing compounds. The next thing we need to ask ourselves now is, why is carbon in all organic compounds? Class, there's no other substance in this world that contains one particular element occurring frequently in all its families. So something was special about carbon. So why carbon? The next question is why. The next question is why carbon? Why is carbon found in all organic compounds? Because this is a big statement to make that organic compounds are carbon-containing compounds. Why carbon? What are the properties of carbon that makes it so special that it's found in all organic compounds? And class, we have 4 special properties of carbon that makes it important in all organic compounds. This course exam is subjective, so every detail is very important because you will not be given options to even remember whether you know it or not. You will just see dash. And when you don't know what to put in that dash, that's where the problem will start. Are we together? So class, it's very important that every detail is mentioned. Why carbon? Number 1, most important special property of carbon that makes it found in non-organic compound is catenation. 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 2, another property of carbon that makes it found in all organic compounds is ability to form multiple bonds. Class. Carbon is so special that he has a family that has single bonds, he has another family that has double bonds, he has another family that has triple. No other element is versatile like that. So if you're an organic compound, you have single bond, carbon there for you. If you're an organic compound that has double bond, carbon there for. You're an organic compound that has triple bond, carbon still there for. So carbon is versatile. Some elements cannot exist double bonded. Like hydrogen cannot exist double bond with someone because it can only take 2 electrons. So hydrogen cannot even be in all organic compounds. Because hydrogen can only take 1 bond. So you see, not all elements can take all these bonds that carbon can take. Ability to form multiple bonds. Another special property of carbon that makes it found in all organic compound is the ability to form ring. Class, the same carbon can form straight chain, can form ring, can form homocyclic, heterocyclic, aromatic, homoaromatic, heteroaromatic, bicyclo. The same carbon can form bicyclo. In fact, this same carbon can form into what we call a staggered conformation. When you get to 200 level, you still continue organic chemistry. So we call a staggered and an ellipse conformation. Just remember this one I said. We have staggered and we have ellipse conformation. This same carbon can form a boat or a shoe structure. These are from 200, 300 level. Start doing those things. Well, let's stay online. Now, ability to form rings. So carbon can form cyclo compounds, and even fuse can form bicyclo compounds. And 4 class is hybridization. Class, carbon can undergo hybridization. I will explain all these things step by step. And by the time you are done with this, the organic chemistry is demystified completely. There's nothing difficult in organic chemistry. Now, these are the 4 special properties of carbon that makes it present in all organic compounds. Now let's start with catenation quickly. what is catenation? Are we together, class? Let's write that. Catenation is the ability. Catenation is the ability of carbon to form long chain structures, continuous long chain structures with each other. Ability of carbon to form continuous long chain structure with each. Class, it's only carbon that you can see. When you start going deeper into organic chemistry, you start finding compounds that have carbon without any break, and they are not bound of each other. Carbon. Every other element would have said bring the other element and see only carbon that is there. We have over 110 elements. Why only carbon? So carbon has the ability to keep bonding with itself without being bored or tired. Carbon, forming long linear chains. That process is known as catenation. The process of doing this is known as what? Catenation. So this is the first special property of what? Carbon. 2. The second property of carbon that makes it found in all organic compounds is the ability to form multiple bonds. Class, when we come to, remember we already have an outline of what we're doing. Number 5 says introduction to alkanes. Class, these alkane families are known by their single bond nature. These alkane families are known by their double bond, and these alkyne families are known by their triple bond. Class, it's because of the versatility of carbon that makes this possible. It is the versatility of carbon that makes this possible, class, that we can have a family called the alkanes because they are only single bonded, and we have a family that are called the alkanes because they contain what? Single and double bonds, and we have a family that we call alkynes that contains what? Single and triple bonds. Class, because carbon can have single bond and be in an alkane family. It can have double bond, we call it an alkane family. You can have triple bond, we call it an alkyne family. So this is, in fact, this is the ability of carbon to form multiple bonds that gives rise to the first 3 families of organic compounds, which is alkane, alkanes, alkynes, which we'll come to later. The ability of carbon to form multiple bonds is what gives rise to the first 3 families of organic chemistry, organic compounds. Alkanes, alkanes, alkynes. And the last but not the least, hybridization. Carbon has the ability to undergo what? Hybridize. And what is hybridization, class? Hybridization is the interaction between 2 orbitals of carbon to form equivalent new orbitals. Interaction. Please, if you are seated and you are seeing someone that is not writing beside you, and you also follow that person, you might not be helping yourself because some of these things have been taught earlier. So please, you see they are laughing. Between 2 orbitals of carbon, so this is the second time I'm taking this course from the beginning again. So be careful who you are watching or you are following. Interaction between 2 orbitals of carbon. So people are just waiting to hear something new, then they add it to their notes. Why you are not even writing at all? Interaction between 2 orbitals of carbon to form equivalent new orbitals. Interaction between 2 orbitals of carbon to form what? Equivalent new orbitals. So when the 2 orbitals of carbon interact or mix and they form new orbitals, that's what hybridization, class. The hybridization, if you go back, let's go back to our inorganic chemistry and so that we can understand what happens in hybridization. Because hybridization is an aspect of inorganic chemistry where we talk about orbitals. Class, if we have to write down the electronic configuration of carbon in the SPDF format, carbon is number 6 on the element table. It becomes hydrogen, helium, lithium, beryllium, boron, carbon. Class, number 6 means that we are writing the SPDF configuration. I'm intentionally saying SPDF because we also have electronic configuration, which is you just say 2, 4. That is the shell configuration, K and L shell, right? For class, we're talking about this is shell configuration. We're talking about electronic configuration, which is 1s2, 2s2, 2p2. Please, if you're watching this video and you don't understand configuration, there's another video that completely explains configuration on our channel. You can go there and watch it. Now, this is the configuration of carbon. 1s2, 2s2, 2p2. Class, you see that in the inorganic chemistry, there's no interaction between the s and the p orbital. Everybody's separate. Everybody's what? But class, in organic chemistry, something can take place between this s orbital of carbon and this p orbital of carbon. And once these two orbitals interact, an hybrid is formed, because an hybrid means you're not really the normal thing that we know. Imagine if goats and bats copulate. Whatever is going to be born will be an hybrid. No, it's not normal, right? Goats and bats. How would the flying goat, would it be a flying goat or a flying, you understand? Or a stubborn bat? Do you understand? It's going to be an hybrid. So when an two s orbital interacts with a 2p orbital, 3 different types of hybrid orbitals are formed, depending on what happens. Because class, remember in organic chemistry, this s block, the s orbital actually has 1 block from your inorganic chemistry. Please, if you still have issues understanding this aspect, you can revisit a previous video when we taught hybridization and electronic or SPDF configuration. This p orbital is known to have 3 blocks. Last, in chemistry, p orbital is known to have 3. So if you are feeding electrons following on through, you should be singly before pairing, of course. If you are feeding electrons in this p block, we have only 2 electrons available. You fill singly before pairing. But there are only 2 electrons, so even 1 block doesn't even have any electron. Class, hybridization in carbon is when there's a movement of this electron to this side, so that we now have this block with only 1 electron, and this block now, each block now has what? 3 electrons. Don't forget that this is an S, right? And this is P. And this P actually has PX, remember? PY and PZ. So class, once this has happened, the real hybridization now starts. When S can choose to interact with PX, PY, and PZ. If this S chooses to interact with PX, PY, and PZ, that means all the P blocks, we are going to have over an sp3 orbital. If this S interacts with all the P blocks, we're going to have what? But if this S interacts with only 2, what are we going to have? And this S interacts with only 1, what are we going to have? SP. This is the foundation, and this is what gave rise to sp3, sp2, and sp. The students are just saying it, alkene, sp3, sp2, but they don't even know what brought about all these things. Now, class, follow me. Let me now show you how sp3, sp2, and sp are also representing the 3 major families of organic chemistry: alkane, alkenes, and you cannot introduce organic chemistry without mentioning alkane, alkene, and alkyne. They are the family, they are the foundations, they are the godfathers of organic chemistry. Alkane, alkenes, and alkynes. Class, remember that sp3 was formed when S interacted with all the 3p, right? Therefore, sp3 families are usually only single bonded, because all the p orbitals have been hybridized, have been what? But class, in the sp2, the S only hybridized with ps and py. So there's one unhybridized orbital remaining. There's one what? Unhybridized orbital. Class, is this extra unhybridized orbital that leads to the formation of an extra bond? This is why sp2 compounds have what? A second. Because there is a base bond for everybody, normal bond. But class, in sp2, only 2, p and ps and py, hybridized. It's pz that is responsible for the second bond yet. That will say sp2 as double bonded compounds. And class, in sp, remember there is a base bond before. In sp, S only hybridized with px, so py and pz are unhybridized, meaning they are going to have double bonds, two more bonds. This is what explains why an sp3 compound is single bonded, sp2 is double bonded, and sp is what? Triple. Class, this sp3 are alkane family. Anybody that is sp3 hybridized is an alkane, sp2 is an alkene, and sp is an alkyne. This is what gave rise to alkane, alkane, and alkyne. Alright, so as we said, this is how the sp3, the sp2, and the sp hybrid orbitals came about. So the sp3, sp2, and sp hybrid orbital were formed due to the what? Due to the what? Interaction between the s and p orbital of carbon. Due to the interaction between the s and p orbital of what? Carbon. Please permit me to repeat this one more time, because my microphone was off when I was saying the last time, and people watching might not really follow. Because anything I said when the microphone was off wouldn't have been heard. Just like some acting drama. Now, so we have one electron here and we have 3 electrons here. Remember that carbon has s and p orbital because the electronic configuration of carbon is 1s2, 2s2, 2p2. The electronic configuration of carbon is 1s2, 2s2, 2p2. So, class, this is the interaction between the 2s orbital and the 2p orbital is what we are after. Like I said, this s has 2 electrons, which is 1 and 2. This p has 2 electrons, which is 1, 1. But there's a block here that doesn't have any electron. So one of the electrons here moves to this point, and then this guy now has only 1, and everybody else has 1, 1 each. And then hybridization starts. When the s orbital interacts with all the, because we have px, we have py, and we have p. Each of these p blocks have a name: px, py, and p. Like I said, if you have an issue with orbitals, you can go back to there are some videos on my channel that helps explain orbitals very well. Now, class, what happens is that when this s orbital interacts with all the p blocks, px, py, and pz, it will lead to the formation of sp3 hybrid orbital. But when this s orbital interacts with just 2 blocks, it will give the formation of sp2. And when s interacts with only px, sp. But what happens is that in the first case, when sp3 is formed, when s interacts with all 3 blocks, sp3 orbital is when a single bond is formed. A single bond is called a sigma bond. It's called what? Because I didn't mention that because it's still we're still listening. Each time you teach, there's always something you can always add. A single bond is called a sigma bond. Any extra bond on a single bond is called a pi, but it's called what? So the first bond in every organic chemistry structure is sigma. The first foundational bond is sigma, and is the strongest. But after the sigma bond, any bond after the sigma bond is not as strong as the sigma. Sigma is known as the strongest. So pi bond. So it means that an sp2 alkene family will have 1 sigma and 1 pi. An alkyne family will have 1 sigma and 2 pi. Class, sigma bond cannot occur 2 times on the same place, like 1, 2. So class, once you see one bond, there's only 1 sigma can be there. Every other person on top is pi. Pi can replicate. But sigma is the first base bond. So class, I was about explaining how this second bond came about in sp2 and why there's no second bond in sp3. In sp3, why there's no second bond is that class, all the px, py, and pz have been hybridized, so we have sp3. But in sp2, only ps and py are hybridized, so this pz is unhybridized because this sp only this and this. So one person was not hybridized. It's this person that was not hybridized that led to the formation of the extra bond. Now in sp, s reacted with only px, that's why it's sp. So py and pz are not hybridized, so we're going to have 2 bonds. 2 extra pi. Very important. Now moving forward, we have explained the 4 reasons why carbon is found in all organic compounds. We've explained the four reasons why carbon is found in organic compounds. So that means we have defined the organic compounds. We have given the history of the organic compound by telling you what F. Waller did in 1828. And the importance of organic chemistry, of course. Organic chemistry is about half of chemistry because without organic chemistry, a lot of things we not have today. In fact, the importance of organic chemistry cannot be emphasized. It can't be emphasized at all because almost everything, I can name anything. This chair you're sitting on is from a tree which is an organic substance. The wood that was used to make this chair was from a tree, which is an organic substance. A lot of things we can refer and say this is why organic compound is very, very important. Organic chemistry is very, very important. The next thing we want to go to now is composition of organic compounds. Composition of organic what? Compounds. Class, in composition of organic compounds, we aim to study what are the other substances present in organic compounds. Class, we have praised carbon so much, we have dwelled so much on carbon that other elements are now feeling jealous. Because, it's the only carbon, what of me hydrogen? I did here. We just call carbon since. Oxygen, I did here too. I know I know 2 days, but I did. I went together class. So, you see the other elements can also play vital roles in carbon. Carbon, a tree cannot make a forest. Carbon cannot just stand on its own. As important as carbon is, class, without any other element, organic compounds will not still be formed. Carbon cannot just be on its own because, class, after carbon has bonded, you still need someone to complete it because carbon is tetrahedral in nature. It's tetrahedral in. So you still need someone to come here. Even if you put carbon here, you still need someone to, except you keep putting carbon. You still need someone to come here. Hydrogen must come here. Hydrogen must. No matter how much you keep putting carbon to fill up, at a point we will get tired and you want to put someone. So class, Other elements are important. So in composition of organic compound, what we do is that in composition of organic compounds, we try to study and test for the presence of other elements in organic compounds. Which other elements are found in organic compounds? So we are sure of carbon now. So in composition of organic compounds, you see what we call elemental analysis. Elemental what? Under composition of organic compound, we call elemental analysis. And what do we do in elemental analysis? We analyze an unknown organic compound to test for the presence of key elements in the organic compound. Elemental analysis is a procedure or a process, experimental procedure, whereby what? An unknown organic compound, and what? An unknown organic compound is tested. An unknown organic compound is what? Tested for the presence or absence of what? Key elements in the organic compound. So we test an organic compound for the presence or absence of what? Key elements. And an organic compound is tested for the presence or absence of what? Key elements. And class, when you want to test an organic compound, there are two types of tests. Class, if you come back here, you see where I wrote qualitative and quantitative analysis of organic compound. We have what we call qualitative and what? Quantitative analysis of organic compound. So there are two types of tests of organic compound. We have qualitative, let me bring it out here. Qualitative and quantitative. So class, in qualitative analysis, we are checking for the presence or absence of an element in an organic compound. So is it are you there or you're not there? But class, in quantitative analysis, so class, the key thing is, follow me carefully, you must have carried out qualitative before you go to quantity. Class, the answer in your qualitative will determine whether you should do quantitative. For quantitative means how much of the element is present in the organic. Now, you don't need to check how much. If you have checked quality and it's not there. So qualitative tells you, is it there, yes or no. So qualitative, the answer is either yes, it's present, or no, it's not. If you have done qualitative and you find out that this element is not present in the organic compound, do you need to go and do quantitative again? Imagine someone said, please go and check that box. Count how many, there's no chewing-gum in my bag, but count how many chewing-gums are inside the bag. You said there's no chewing-gum in your, but still count it now. You know they follow instruction. And you know, count how many chewing-gums are in that bag. How? You said there's no chewing-gum in the. So you cannot do quantitative analysis when it's not even. So you carry out qualitative to find out whether it's present or. If it is now present, you now forge ahead to what? Quantitative will now test how much of the element is present in the organic. So if we were to define it, you say qualitative analysis of what? Organic compound, whereby what? The organic compound is tested for the presence or absence of key elements. Organic compound is tested for the presence or absence of what? Key elements. I know why I said key element, because it's not all elements that still exist in organic compounds. So we're going to be looking at key elements. The key elements that we'll be looking at, number one, after carbon, the most popular element in organic compound is hydrogen. Is what? So please take note. And after hydrogen, oxygen. Then the halogens are popular with organic compound. The halo what? That is the group 7 family of the periodic table. The halogens. The chalcogens, okay, the chalcogen, oxygen. Okay, oxygen is a chalcogen, but let's see oxygen, sulfur. So what? Then we also have the group 5 element, which is the nitrogen family. Nitrogen family, that nitrogen and the rest of them. So we're looking at tests for nitrogen, sulfur, oxygen, halogens. These are major people will be testing for. These are the most popular elements in organic compound, apart from carbon. After carbon, the next assistant boss is hydrogen, oxygen, then you have the halogen, sulfur, nitrogen, yes. So these are the people we'll be testing for. So someone should not tell, are we going to test for all the 110 elements? When we finish this one, no. These are the key elements we are testing. Or even if you check the test, these were the key elements that were tested 4. So we're going to be teaching you qualitative analysis first, then we'll then move to quantitative analysis. Class, are we following? Are we following? So, above on the board here, remember when I told you about the German scientist, F.O. 1828? And I just thought you could be asked to write down because it's a subjective exam, you could be asked to write down the arrangement reaction that occurred that made ammonium cyanide turn to what? Urea. This is the reaction. This is the reaction. That's what everything I'm saying is in your textbook. I know I was in your textbook, but I know everything inside this textbook. This is page, this page 2. So this second page is already there. For someone that has not read well, will not even know, you just want to sit in exam. Which one be F4 like again? You know that is in your textbook. Anybody person on drawing structure, I can draw structure, I can name. Simple thing that you just underrate it. Page 2. How ammonium cyanide was rearranged to give what? Urea. Please, we're just digressing a bit, but let's go back to what we're supposed to do. So please, in case you ask to write the rearrangement reaction, express the rearrangement reaction of how ammonium cyanide was rearranged to give what? Urea. So your textbook, I got to page 2. Yes. Because please, what I want to tell you that this exam, what you think will come out is not what will come out. The way many people are just hyping structure, but give me structure, I go draw. Give me name, I go name them. There's more other things. Like, was it last said? He just broke one very funny thing. RF factor. I believe it's addition factor. This addition factor is under separation techniques. Most students did not read it. Separation techniques of organic compounds is chromatographics. If you go to chromatographic methods of organic compounds, some people just that one affects they know if he has that. This is not main organic, and I leave that one. Retardation, they say calculate the retardation factor. Which if those that attended the first marathon, I thought this. If you check your notes, maybe you forgot it now, I'm sure over the weeks you've already used practical and cover everything. But check your notes, you see it. Retardation, I'll teach you again, don't worry. All together, that's one thing I people know that, but this is not draw structure, this is not name, it's calculation. Calculating the retardation factor is a chromatographic technique. So please, on common stuff like this, don't give all your time just drawing structure. If you must have learned from first semester exam, you say that some things you expect in those you just brought another some funny things that you didn't read. So think outside the box when you're studying this time around. Because let you also know that you are trying to preempt them. You're trying to predict what they will bring out. So moving forward, please, viewers, sorry for the digression. Let's continue now. We're talking about elemental analysis of organic compounds, and we said we will focus first on the qualitative. Because if the element is not present, there's no way we can calculate how much of it is present. So class, qualitative analysis of organic compound. And first, the first two compounds we look at are the boss, which is carbon and hydro. This is another important aspect of organic chemistry. Some people don't want to take time to know, but it doesn't have anything to do with draw structure, because it gets to the point that the course start being interesting. Draw the structure, that's why people don't jump to that aspect. There's a lot of marks to pick up in this aspect. It's not about the one that's interesting, it's the one that will give you your mark. So as I said, those topics that are boring, take note of them. They're the ones that are unexpected. Carbon and hydrogen. Let's look at the study, the qualitative analysis of carbon and hydrogen and organic compound. How can we test? Of course, we know that there's no organic compound without carbon, right? But there's still a test that can be carried out to confirm that carbon is actually there. As a matter of fact, this test is important actually, right? Because it means if you want to do something as an organic compound, what do we do? Just test for carbon, right? So someone might, because I'm just saying this to answer someone that might say, why are we testing for carbon again? I thought carbon is non-organic compound, right? But what if you didn't know whether the compound is organic or they just gave you a compound and said, check, is it organic? What will you now do? You need to test for the presence of. So the first two things we look at, how to test for the presence of carbon and hydrogen in an organic compound. Let's go quickly. So write down the unknown organic compound. So we've got the organic compound unknown because we don't know yet till we confirm it. The unknown organic compound. The unknown organic compound is estimated. The unknown organic compound is estimated by mixing a known weight of the compound. The unknown organic compound is estimated by mixing a known weight of the compound. The unknown organic compound is estimated by mixing a known weight of the compound with dry copper 2 oxide. With dry copper 2. The unknown organic compound is estimated by mixing a known weight of the compound with dry copper 2 oxide, CuO. The unknown organic compound is estimated by mixing a known weight of the compound with dry copper 2 oxide, Cu, and heating the mixture in a test tube, and heating the mixture in a test tube, and heating the mixture in a test tube. And heating the mixture in a test tube. The unknown organic compound is estimated by what? By mixing the known weight of the compound with dry copper 2. What's copper 2 oxide? CuO. And heating the mixture in a what? Test tube. If carbon is present, it is oxidized. Write down. If carbon is present, it oxidizes to carbon dioxide. Class, if carbon is present, it will be oxidized to what? Carbon di. So this CuO is to what? Is to test if carbon is there. If carbon is present, to what? It will be oxidized to what? Carbon dioxide, which is CO2, right? If carbon is present, it will oxidize to what? Carbon dioxide, CO2. If carbon is present, it is oxidized to what? Carbon dioxide. If carbon is present, it is oxidized to carbon dioxide, CO2. And is detected, and carbon is confirmed, class. So if CO2 is formed, class, it is very observable because CO2 is a gas, right? Evolution of gas, right? So anything that makes you carry an organic compound and react to dry copper 2 oxide, and you see a gas, evolution of gas, and you confirm that it's CO2. So this is a gas is a form, but it could be any gas. To confirm that it is CO2 plus, to confirm that it is CO, we bring in what we call lime water. Lime water is calcium hydroxide solution. Calcium what? But it is a known fact in chemistry world that CO2 will turn lime water milky. CO2 does what? Plus, once this lime water becomes milky, it's a confirmation test that it was CO2 that was evolving, because it could be any gas, right? So to confirm that this was CO2, because if it is CO2, then it tells us that it's carbon, right? Lime water turns milky. Please take note, in case I was too fast or I was not clear enough, just to be clear, please. You take an unknown organic compound. We are testing for carbon and hydrogen, right? But it's obvious that we're starting with carbon first, right? So everything we are doing now is just for carbon. We'll come to hydrogen. What did we do? We took the unknown organic compound with what? Reacted with what? Carbon, copper 2 oxide, copper 2, it is in a mixture in a test tube. What happened? A gas is evolved, CO2 is formed, because if carbon is in an organic compound, it will be oxidized to CO. If carbon is there, that's what? But now, when the CO2 comes out, now it's because we're doing it theoretically, I say CO2. In the lab, we will not know whether it's, you just see gas, have you? You don't know whether it's CO2 or not until you now introduce what? Lime water to confirm which gas is this. Because if it's any other gas, then it was not carbon that was present. But carbon will not just bring out any other, it will bring out CO2. So what you do, you introduce lime water into the reaction mixture, and if CO2 is there, it will turn the lime water. You know when something is, imagine, you know when something is milky, right? And when something is just normal water. So if this lime water starts turning milky, it just confirms to you that it was CO2 gas that was going out. And if it is CO2 gas that's going out, the only person that can oxidize CO2 is carbon. So carbon is actually present in the organic compound. Does this make sense? I'm sure that those that were in the first class, this should even bring more clarity, right? Okay, this is what I was saying then. Okay. Why those that were not in the first class, you're still getting it now. So it's a win-win for everybody. Now, follow me. And we've confirmed carbon. So carbon is present, right? Let's now go to, how do we now check if hydrogen is what? Present. How do we check if hydrogen is what? Present. Class. This same carbon, copper 2 oxide. Who remembers that copper 2 oxide causes carbon to be oxidized to CO2, right? If hydrogen is present in the organic compound, it will cause hydrogen to be oxidized to water, H2. So why carbon is oxidized to CO2, hydrogen is oxidized to H2. Why carbon is oxidized to CO2, hydrogen is oxidized to what? H2O. So this copper 2 oxide helps us to bring out both carbon and hydro. So we react a unknown compound with copper 2 oxide. If carbon is present, it goes to CO. If hydrogen is present, it goes to H2. When carbon went to CO2, we now did something else to confirm that it's carbon, right? Who did we use? Lime water, right? And it turned it milky. So when hydrogen goes to H2, we need something to confirm that it is water. Because it's not only water that is colorless. And you cannot say, let me drink it. What is acid? You don't go. Are we together? So let me I just drink. I don't get time to the test confirm. I beg. Give me water. I even the test. Are we together? So class, how do we confirm that it's H2 what? Class, we use what we call copper 2 sulfates. Copper what? Copper 2 sulfate is a very good reagent that can help us to know if it is water. CuSO4, copper tetrasulfate 6. Because once copper tetrasulfate 6 meets water, it turns blue. It turns what? Immediately. Once this CuSO4 meets water, normally it is white. It is what? But as soon as water is there, no other person will turn blue. So we know that it's water that must have done this. So if this guy turns any other color, if he turns the color of your shirt, know that it's not water. You must turn what? Blue. You must turn blue. So class, water will turn this CuSO4 blue. And that confirms the presence of water. Class, just this blue can be 2 marks in the exam. What you follow is the correct color is subjective. Subjective means that lecturer has the right to ask from anywhere. Which you follow is the correct color change of copper 2 oxide during elemental analysis of a non-organic compound of hydrogen. You'll be thinking, give me structure now. Which one will be this one? Give me structure. Give me structure. I'm ready. Structure. Because there's no structure today. Give me color. Because lecturer knows that everybody is jacking structure. I can name. Give me, I can name them. They know, just like first semester. But it doesn't mean you should not abandon structure. Everything will be taught, obviously, but I want us to also make sure that we are prepared for if they switch that, they give us something that is not expected. We have just tested for carbon and hydrogen. Let's now go to test for nitrogen, halogen, and sulfur. Remember that the other elements we need to test for nitrogen, halogen, and what? Nitrogen, halogen, and sulfur. Let us test if these three are present. Nitrogen, halogen, and sulfur. Test for nitrogen, halogen, and sulfur. Test for nitrogen, halogen, and sulfur. Don't forget everything we are still under what? Qualitative analysis. Qualitative analysis. Let it. Class. Test for nitrogen, halogen, and sulfur. Class, to test for nitrogen, halogen, and sulfur, there's a special name for the test. It's called the sodium fission. Sodium what? Please do not forget it. It's a popularly asked question. But doesn't mean that it will come out again. It's also called Lassagne tests. Another name for sodium fission test, please note, is Lassagne test. Please take note. Class, I haven't written this down. Let's tell you what happens during sodium fission test. Class, the sodium fission test, as the name implies, the unknown organic compound, you take it again, because the organic compound should be unknown. You can test for something that you know already, then you're wasting your time. You already know it now. The essence of experiment is to check what you don't know, to know it, Abby. So that's what we're calling the unknown organic. So the unknown organic compound, unknown. Has this happened to you before? You think you are wrong with the spelling? Is this correct?
Yes.
This is unknown. Looking wrong in my eyes. It happens, right? We spell it something, but am I getting it? Looking where? Unknown organic compound. The unknown organic compound is fused with sodium. Fused with what? That's why it's called sodium fission. Fused with sodium. Sodium fusion. In an ignition tube, in an ignition. The non-organic compound is fused with sodium in an ignition tube. Class, why sodium? Because sodium, if you notice these elements we are testing for, class, look up. What is common among all these elements we are testing for? The nitrogen, halogen, and sulfur. They are all. No, they are not all group 5. Now this is group 5, this is group 7, this is group 6. They are all electronegative elements. They are all what? Nitrogen is electronegative. What are electronegative elements? Elements that will gain electrons to become negatively charged, right? Elements that will gain electrons to become negatively. Nitrogen will gain electrons to become negatively charged. But nitrogen is number 7 now, which is 2, 5, 2 what? So normally it's easier to gain 3 than to lose 5, right? Remember those octets chemistry now? Gaining 3 means that it's not N3. Halogen, chlorine is 287 obviously now. You just gain 1, Cl. Sulfur is 286, gains 2, S2. They are all electronegative. That's why I said the question is why sodium? Why? Sodium on the other hand is what? Electropositive. Sodium is 281. 28 what? Sodium is electropositive. What happens to unlike charges? Unlike plus, we always attract minus out if you are inside. Plus, we always bring out every minus inside the organic. We want to bring that when you're testing for something, you want to bring it out. Come out. If you are there, come out, let me see you. So what happens is that sodium fused to the non-organic compound is a positive person coming to where they are many negative. Even the negative, they are tired of each other. They saw one positive, they will rush to the positive, right? Because they are out there just negative, negative here. So you just throw one positive into the mix. The rush. Nitrogen immediately is converted to cyanide ion. Converted to what? Immediately sees sodium, it's converted to cyanide. This is an exam question. Nitrogen is converted to cyanide. During the Lasagna test, nitrogen is converted to dash. Halogens are converted to their respective allied ions. Halogens are converted to their respective what? Allied ions. And sulfur is converted to sulfide ions. Now when I say halogens are converted to respective allied ions, why I say respective, there is not only one halogen we have. We have chlorine, right? We have bromine, we have iodine. So there are a lot of halogens. So if it's someone like chlorine, chlorine is converted to what? Chloride ion. Bromine is converted to bromide. And iodine is converted to what? Iodide ion, I minus. So it is Cl goes to Cl minus, Br goes to Br minus, I goes to I. But the most important obvious change is nitrogen to what? Cyanide. Because the other ones are straightforward now. Chlorine, chloride. Nobody will ask you down on chlorine, chloride, except the lecturer was sleeping when I was setting it. Bromine, bromine. It's too straight. I think this is the catch. Sulfur, sulfide. Class. That's the first step. So sodium has brought them out. So what happens is that we're now going to have this cyanide is going to become sodium cyanide, right? NaC. If any of the allied NaCl, chlorine, or NaBr, and the sulfur, Na2S. So this is all the things that are formed. Sodium cyanide is something nitrogen is present. If chlorine is present, sodium chloride is formed. If bromine is present, sodium bromide is formed. If iodine is present, sodium iodide is. If sulfur is present, sodium sulfide is. If they are all present, right? Any of them that was not formed, no, that is not present. It's not what? But as usual, we have to do confirmation, right? If you notice every test you have been doing, after putting one, then you go now to confirm that it's this guy that came out. Now moving forward, class. To confirm the presence of each of these components, we have different methods for each of them. Halogens. For the halogens class, we introduce what we call silver nitrates. Silver what? AgNO3. Now, why silver nitrate? Why what? Because the silver in silver nitrate has high affinity for the halogens. So, class, sodium has done its job. He has brought out everybody, have you? So So everybody go and find out you not confirm if you are present or not. So when I say let's pick halogens first, right? Do not forget we are testing for nitrogen, halogen, and sulfur. Sodium has brought all of them out. Sodium brought nitrogen as cyanide, halogen as the respective halides, and sulfur as sulfur. To now confirm the test, we will start with halogens first. We are starting with halo to confirm. For the halogens, we then introduce silver nitrates. Class, silver nitrate, because the silver in silver nitrate has high affinity for the halogens. As a matter of fact, once silver spots these halogens, where are the halogens? Okay, let's look at the halogens. Remember that for the halogens, what are the halogens? NaCl, NaBr, NaI. Class, immediately, this silver will replace the sodium immediately. Immediately, silver replaces this sodium. And what is now formed is a silver chloride precipitate or silver bromide precipitate or silver iodide. A precipitate of silver halide is formed. If it is chlorine, there's a color we are going to see. If the precipitate color is white, just know that it's chlorine that is formed. This can also be asked, but the colors are different. If the precipitate color is pale yellow, pale what? Or yellowish white. Just know that it is bromine, precipitate. If you notice any precipitate, PPT is precipitate, right? And if it's pure yellow, full yellow. Yellow precipitate tells me that it's what? Iodine is formed. These are the parts that most of them might not take time to sit down because reading a book without God this theory is boring, I must admit. When you have assignments to submit, you have work to fill, you have lectures, practicals. I'm not sure any student has sat down this semester and just been reading this thing like this. Let all the structures that because even when you can see people drawing structure, that one has attention. But someone just sit down and start reading all these things. That's why I must be very patient. But they're in your text, you can see I'm using your text, they're in your text. Chlorine, white precipitate. Bromine, pale yellow or yellowish white. If it's iodine, thank God for the color changes because all of them are all halogens. So if they all go different color, how will we know who is? So this confirms the exact halogen that is present in the non-organic. So the same 2 marks that you will get from drawing one big structure in your exam, the same 2 marks that this white will give you. For each question carries 2 marks, 35 questions, 35. Each question carries 2 marks. So that means that draw the biggest structure is still 2 marks. As long as like white, same 2 marks. Now class, follow me now. We have now tested for all halogens. It's now time to go and confirm the presence of nitrogen. How do we now confirm the presence of what? Nitrogen. Remember that what we are doing is confirmatory test. We have already tested that they are there in a way. We have sense that they are there because they have all been converted. Sodium brought them out, right? So we have, it's like they are there, but we want to confirm. That's what we are doing here. Now let us confirm, we have confirmed halogens now. We've confirmed, let's confirm nitrogen, let's confirm nitrogen. Let us confirm nitrogen. It's now time to test to confirm the presence of nitrogen. Please, if you're following us, keep following us. It's now time to confirm the presence of nitrogen. Do not forget that nitrogen stopped at sodium cyanide, where nitrogen's journey stopped, right? Because in a non-organic compound, sodium was introduced, and if nitrogen is present, it comes out as cyanide. Remember, if nitrogen is present, it comes out as what? Cyanide ion. We then react with the sodium that was fused to form was sodium. Please, are we still following? Yes. Now, so from the sodium cyanide now, what we do is that we introduce what we call ferrous sulfate. Introduce what we call what? In the example, name the reagent introduced to confirm the presence of nitrogen during the last stagnate test. Name the reagent, it's subjective. Name the reagent introduced to confirm the presence of nitrogen during Lassagne test. Ferrous sulfate. So in that marathon write-up, when I said that likely exam questions would be, this is what I mean. I say every time I teach, I think of how can it question be asked on this aspect. So it's one thing to know a topic, it's one thing to not prepare exam-wise for that topic. Ferrous sulfate, of course, the chemical formula is FeSO. So what happens? Follow me now, let's go. Write down please for those that are writing, those that have not been in the class in the beginning of the semester, write down. Ferrous sulfate is introduced which converts the sodium cyanide, converts the sodium cyanide to sodium ferrocyanide. Converts sodium cyanide to what? The sodium sulfate introduced converts sodium cyanide to sodium ferrocyanide. The sodium sulfate introduced converts the sodium cyanide to what? Sodium ferrocyanide. And a Prussian blue precipitates. A Prussian blue what? Precipitate is formed. This Prussian blue precipitate that's formed confirms the presence of nitrogen. This Prussian blue class, it's recently I even know that there's some this color called blue, white. There are types of blue. You know that? Types of yellow. Prussian what? Blue precipitates. No, there's a color we call wave. I realize more about the color. There are some colors that we don't know. It's not red, blue. Yeah, but give me red there. There are colors. There are colors. This one, what's the other one? Forgotten. Prussian blue precipitate is what is formed and confirm the presence of nitro. Let us now go and confirm the presence of sulfur. Let us go and confirm the presence of what? Class, this beginning part of the course is boring but necessary. I know I could have easily just jumped to the structure and just be happy. But it's exam we are writing, we are not yet to be happy, yet to pass exam. Sulfur, are we together? Where did sulfur's journey end? Let's see if we are still following. Where did sulfur's journey end before we want to confirm now? So, sodium sulfide, right? So we introduce sodium to the non-organic compound. Sulfur comes out as sulfide. So sulfur comes out as what? Sulfide S2, which reacts with the sodium forms sodium Na2S. So this is where sodium journey, right? From when all of them were together. Why am I reminding you? Because we tested for nitrogen, halogen, and sulfur together by introducing sodium. So this one came out as cyanide, it came out as allyl, it came out as sulfide. Sodium sulfide. Now let's continue sodium sulfur's journey. Class, to confirm the presence of sulfur, we introduce what we call a sodium nitroprusside. Sodium nitroprusside. Sodium nitroprusside is introduced this sodium nitroprusside, which then gives off a violet coloration, confirming the presence of sulfur. Violet what? A violet coloration, and this violet is the color that we all know indeed. Violet coloration confirms the presence of what? Sulfur. 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 Class, now that we have tested that they are now there, question in ourselves is how much of them are, how much of sulfur is present, how much of nitrogen is present, how much of halogen is present in the organic compound. And class, don't worry, the easiest method of finding out how much have of the elements are present is what we call we have empirical and molecular formula. Empirical and what? Empirical and molecular formula of organic compounds. Empirical and molecular formula of organic compounds. Because class, you know the empirical formula is the simplest formula that considers each element in the organic compound and how many atoms of the elements are present. So you will know how many atoms of each element is present. Class, so we're giving you a question now that will ask us to enable us to determine how many atoms of element is present in the organic compound. Let us take this question down quickly. So we know that normally I would have been defining empirical and molecular formula, but because this is an organic chemistry class, it's already expected that someone that is coming from an organic chemistry class already has studied inorganic aspect and can define empirical formula, can define a molecular. But please, if you are watching this video, we don't want to assume that you know it. You can always check out the other videos and you see a class on empirical and molecular formula. Thank you. Now let's move forward to the question now. So for this particular class I'm teaching, I expect that everybody here knows empirical and molecular formula. Let's go now. Take this question down. Let's take a question on empirical and molecular. 0.404 gram of an organic compound A. 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 0.404 gram of an organic compound what? A gave on combustion 0.722 gram CO2, gave on combustion 0.722 gram CO2 and 0.294 gram H2O. Gave on combustion 0.722 gram CO2 and 0.294 gram H2O. Gave on combustion 0.722 gram CO2 and 0.294 gram H2O. What is the empirical formula of A? What is the empirical formula of A? Just to be clear, one more time, 0.404 gram of an organic compound A. So the organic compound is unknown, so it's called A. 0.404 gram of an organic compound A gave on combustion 0.722 grams CO2 and 0.294 gram H2. So it gave H2 of 0.29. We're asked to find the empirical formula of A. Class, usually from our knowledge of inorganic chemistry, if you ask to find empirical formula, usually they will give you the percentage composition of each element, right? They will tell you carbon occurs to 3.8%. They might say hydrogen occurs 32.2%. The oxygen occurs 3%, whatever. But eventually, when you add up all the percentage, you usually end up having 100. And then you then take it from here and start dividing by their atomic mass, right? Carbon is 12, right? Hydrogen is 1. Oxygen is 16, right? This is what you usually do. Now start dividing by 12, divide by 1, divide by. Then you keep dividing by the smallest, you have a O, and you get to empirical. Remember from inorganic. But now, class, looking at this organic chemistry question, does it look like we are giving something like this? No. As a matter of fact, they are not even giving us carbon percentage or carbon mass. They are giving us CO2's mass and H2O mass. And yet you are asked to find the empirical formula of the organic compound. This will take more than your normal knowledge of empirical formula. Please take notes. Now, looking at this, it's clear that we need to first ask ourselves. The question said that the organic compound is 0.404 gram. But when it undergoes combustion, it gave CO2 and H2O. And class, if we add these two masses together, so this compound gave these two. But if you add these two masses together, it's more than the whole mass of the organic compound. So something is wrong some. Because if this is 0.404, but yet it gave 0.7, 0.7 is already bigger than 0.4. Not talk when you now add 0.2. So class, what it means is that during the course of the reaction, it wasn't only the organic compound that played a role in the reaction. The organic compound gave on combustion. Combustion definitely means the organic compound was reacted with oxygen. Reacted with what? So the oxygen brought its own mass and increased the overall mass of the products. Are we together? For class, they know fact that when the organic compound undergoes combustion, two compounds are surely going to be formed, which is carbon dioxide and what? H2. During combustion of organic compounds, the two most popular products formed are carbon dioxide and H2O, water. Please take consideration an exam likely question. CO2 and H2O during combustion. Combustion is what? Oxygen is involved. Boiling of an organic compound, reaction of organic in presence of air, oxygen. So class, if this was 0.404 before the reaction, right? Once it has gone into a reaction, you cannot predict what will happen to its products. That's why the products are higher. But class, from this is products. Before I can get the empirical formula of the non-organic compound, I need to find out how many carbon is in the organic compound. How many hydrogens in organic? Because they call it an organic compound means that you cannot be an organic compound if you don't have carbon. So how many carbon are there? And after carbon, there's no organic compound that does not have hydrogen one way or the other. How many hydrogens also? Then are there any other elements? Because apart from carbon hydrogen, looking at this reaction, which third other element will you think of that should be there? Thank you. Is there oxygen present? For class, oxygen is still under maybe. Oxygen is still under may. Because class, if we find the mass of carbon and hydrogen, and we add it together and it gives us total mass of the compound, it means that no other element is. But we add up the mass of carbon and hydrogen, and it's lesser than this 0.404, which is total mass of the organic compound, means someone else is, and that is likely oxygen. Because of this total reaction, it's only look at the product. What are all the elements that came out in the product? Carbon, hydrogen, and what? So you cannot say this chlorine in this compound, right? You cannot say this sulfur. Where did sulfur come from? It should be shown in the product, right? Ember that did not survive the product stage is not in the reaction. So our three likely elements is carbon, hydrogen. Why is it important to bring out the three likely elements? Because you cannot calculate empirical without bringing elements and their composition. But if you are solving it, just like I showed you, you want to solve empirical formula, you must bring out the composition and start dividing, right? So what is the composition? That is the first question you ask your. When they give you organic chemistry question like say, find the empirical formula, ask yourself what is the compo. And you cannot bring out CO2. CO2 is a compound, it's not an element. When you solve empirical, you don't use compounds, you use LA. Please take note. Now, so class, we need to find how many carbon is in the organic compound, how many hydrogens in the organic, and how many oxygen, if possible, is in the organic compound. Let's start with carbon. To find how many carbons in the organic compound, class, the organic compound is unknown, but we can get it from the CO2. Why? Because class, after A reacted, two products were formed. On one side of the product is only where carbon exists. There's no carbon in this H2O, right? So every carbon that must have been in A must definitely be in this CO2 anyway. Does that make sense? Every carbon that must have been in the organic compound must be in CO, and every hydrogen that must be in the organic compound must be in H2. So we can get the mass of carbon from CO2 and get the mass of hydrogen from H2. How do we go about it? Follow me. Plus, we have the mass of CO2. 0.722. And on this side, we are looking for the mass of carbon, right? We don't know. We don't. For class, on the second step stage, the molar mass of CO2, can it be obtained? Yes. And on this side, the molar mass of carbon, can it be obtained? Our carbon must be gotten from CO2. Class, what is mass of CO2 from the organic compound? 0.722 grams of CO2. Equated to what is mass of carbon? We don't. What is molar mass of CO2? C is 12, right? O is 16, but 16 is occurring twice. O2. 16 times 2. What's 12 plus 32? So on this side, we have molar mass of CO2 40. What is molar mass of carbon? 12. Let us cross. So we're going to have 44 times MC is 44 MC. Equals to 0.722 times 12. We have 0. Now, to make MC straight on the formula, what is MC mass of? Divide both side by 40. Divide both side by what? Whatever final answer we get here will be the mass of carbon in the organic compound. 0.722 multiplied by 12 divided by 44. No, the only thing I'm doing is from your textbook here. I took the question from, it's not coming to my head, from your textbook. What's the answer? Mass of carbon in the organic compound is 0.1969 grams. Let's approximate this 9 to 7. Look at our question was leaving all. Look at lecturers even set the questions when you are solving in science courses. Always follow the pattern your lecturer gives. Look at it's not by coincidence. All of them are all in 3 decimal. So 0.1969 means 0.197 approximately, right? 0.197 grams. We've gotten the mass of carbon. We've gotten the mass of what? This same procedure will be done for hydrogen. For class, in this case, instead of putting CO2 and C, we're going to put in H2O and H. H2 and what? So hydrogen can only come from H2O, right? Carbon can only come from CO2. Hydrogen can only come from H2. Does that make sense? Can I have hydrogen in CO2 here? Where is hydrogen in here? No hydrogen. This is the only way you can get hydro. So using the same pattern, on one side we're going to say mass of H2O. So left hand side is H2O, right hand side is H. Equals to mass of H. Mass of what? Thank God this class is recorded, so you can actually watch again and again and again and get better. Second step is a molar mass of H2O which can be obtained. Equals to what? Molar mass of H. Since we are still writing this, are we done? Can I clear this part? Yes or no, please? Okay, so inquiry out this. Let us now look at this, do the same thing for hydrogen. We've gotten a mass of carbon. Let's put our mass of carbon somewhere. What did we get as mass of carbon again? 0.197. Class, that correct? Now let us get a mass of hydrogen. So the mass of hydrogen, the same method we use to get a mass of carbon, we'll repeat for hydrogen. Mass of H2 equals to mass of hydrogen. And molar mass of H2 equals to molar mass of hydrogen. What is the mass of H2O given in the question? 0.294, right? So we'll say 0.294 grams of what? Of H2O, right? Equals to, what is the mass of H2? We don't know, call it MH. We don't. Now what is the molar mass of H2O? Can it be obtained? And this is the popular number that H2 is 18 grams, remember? Everybody should know that H2O is 18. Molar mass H2 1 times 2 plus O is 16, 18. What's the mass of H2 1 times 2? 2 grams. What we're going to do cross. So we're going to have 18 times MH to 18 MH equals to 2 times 0.29. So what we'll do now is divide both side by 18 to make mass of hydrogen straight of the divide both side by. We're going to say MH2 equals 2 multiplied by 0.294, then divided by 18. What are we going to have? Please, 3 decimal places. 0.33, right? So the mass of hydrogen class is 0.033 gram. Class, we don't need to stress ourselves further now. Since we know the total mass of the non-organic compound class, and we've gotten mass of the two elements, key elements. What we need to do now is to add them together and find out, is it going to give us 0.404? If it gives us 0.404, that already tells us that only carbon and hydrogen are present in the organic. But if it doesn't give us 0.404, it means that oxygen is also. And how do we now get the mass of oxygen? Is by subtracting total mass of carbon and hydrogen from the mass of the organic compound. The remaining must be oxygen. Does that make sense? Yes. If we add the mass of carbon and the mass of hydrogen together, and it doesn't give us 0.404, it means someone else is still inside, right? That's why it's not complete. That person must be oxygen. Let us add up mass of carbon plus mass of hydrogen. What are we going to have? 0.229? 0.229 gram. It's not up to 0.404, right? Meaning that what? Someone else is what? Present. Now, class, follow me. 0.197 plus 0.033. 0.230. Okay. Still not up to 0.404. So if you remove 0.230, 0.404, whatever is remaining must be oxygen. Because we have already confirmed that it's only carbon, hydrogen, and oxygen that is present. So now we're going to say 0.404 minus 0.230. Sorry, you have the class. 404 minus 0.230. 0.174. Class, therefore, this is the mass of oxygen. Mass of what? 0.174 grams. Now the rest is very simple. Now we have gotten carbon, hydrogen, oxygen. Carbon is 0.197. Hydrogen is 0.033. Oxygen is 0.174. What we need to do now is to divide by that atomic mass. Carbon divided by. So carbon is atomic mass of carbon is 12 grams. Remember? Hydrogen is only 1 atom, so it's 1 gram. Oxygen is what? So start dividing by the atomic mass, divide by 12, divide by 1, divided by 16. What we're going to add in this class, there's another class that's holding soon here. 0.197 divided by 0.016. Yes. What I'm talking, this one is just 0.03. 0.01. I like as you gave me in 3 decimal. Now, start divided by the smallest, right? So you're now in familiar territory. We are now in familiar 0.011 divided by 0.011 because 0.01 is the smallest. What are we going to have there? The first one? 1.5. Huh? So 0.017 divided by 0.1 is 1.5. So the carbon aspect gave us 1.5. Hydrogen, what did it give us? 3. And what the oxygen give us? 1. Class. Very important stage now. Follow me so we can round up for today. 1.5, 3, and 1, class. You cannot stop here because you cannot say so. I see 1.5, 8, 3. Oh, class. Your bigger formula must be an whole number. But class, if you keep dividing by the smallest number, which is 1, to keep bringing us back. So once you divide, division can no longer work. You then multiply by the smallest number. Multiply everybody by 1, you have the same thing. After 1, what is the next smallest number? Multiply everybody by 2. You only do this when you have a decimal that cannot be gotten rid of by divided by the smallest. And when everybody is a whole number in a way. So multiply everybody by 2. 1.5 times 2, 3. 3 times 2, 1 times 2. So your bigger formula is now C3H64. And class, we have come to the end of today's session. We are going to continue tomorrow. Please, if you missed today's class, do not miss tomorrow. You're following this class and you gain something from today's class, kindly subscribe to our channel to get more videos like this. You have challenges in physics, chemistry, mathematics. There are more videos that can help you understand and break down these concepts very well. Okay, thank you very much.